In this tutorial, we'll build a neural network using TensorFlow to classify clothing images from the Fashion MNIST dataset. The next step is to import TensorFlow, NumPy, and Matplotlib. This will be used for building machine learning models, performing numerical calculations, and creating graphs or visualizations. The next step is to load the training and testing datasets into Train X, Train Y, Test X, and Test Y. The training data will be used to teach the model patterns and relationships, while the testing data will be used to evaluate how accurately the model performs on unseen data. This step is important because machine learning models require organized input and output data before training can begin. The next step is to create class names for each category in the dataset, such as t-shirt, trousers, pullover, dress, coat, sandal, shirt, sneaker, bag, and ankle boot. These class names make the output easier to understand because the model's numerical predictions can be converted into meaningful clothing labels. The next step is to normalize the data by dividing the pixel values by 255. This converts all image values from the range 0-255 into a smaller range between 0 and 1, which helps the model learn more efficiently and improves training stability. Display the first image from the training set using Matplotlib. You can use plt-imshucks train 0, map equals gray, to show the image in grayscale. This helps you visually confirm what the dataset looks like before training the model. Then the training and testing image data is reshaped into a 4D format using -1, 28, 28, 1, where -1 automatically calculates the number of samples. This converts both train X and test X into proper CNN input shape, with each image size 28x28 pixels in a single grayscale channel, allowing the model to process batches of images correctly. The next step in building a Keras model for the Fashion MNIST dataset is to construct a convolutional neural network, CNN, that can effectively learn patterns from images. This is done by stacking different types of layers in a specific order, so the model can go from simple feature detection to final classification. You begin with a conv2D, convolutional, layer, which scans the input image using small filters. These filters help the model detect basic visual features such as edges, corners, and simple textures. For Fashion MNIST, this is important because clothing items like shirts, shoes, and bags are distinguished by shapes and outlines. After this, you typically apply a ReLU activation function to introduce nonlinearity, allowing the model to learn more complex patterns. Next comes the max pooling 2D layer, which reduces the spatial size of the feature maps. This step keeps only the most important information while discarding less useful details. It also helps reduce computation and makes the model more robust to small shifts or distortions in the image. Pooling essentially summarizes regions of the image so the network becomes more efficient. After the first block of convolution and polling, you usually add a second conv2D layer. This layer learns more advanced features by combining the basic patterns learned earlier. For example, instead of just detecting edges, it might begin to recognize shapes like sleeves, collars, or soles of shoes. This is again followed by another max pooling 2D layer, which further compresses the data while preserving key features. Once the convolutional layers have extracted useful information from the image, the output is still in a 2D feature map format. To prepare it for classification, you use a flatten layer, which converts the 2D data into a single long 1D vector. This step connects the feature extraction part of the network with the classification part. After flattening, you add a dense, fully connected layer. This layer acts like a traditional neural network and learns combinations of the extracted features to make better decisions. It helps the model understand relationships between different features and refine its predictions. To improve generalization and reduce overfitting, you then include a dropout layer. During training, dropout randomly disables a fraction of neurons, which forces the network to not rely too heavily on any single feature. This makes the model more robust and improves performance on unseen data. Finally, you add the last dense output layer, which has 10 neurons, one for each Fashion MNIST class. This layer uses the softmax activation function, which converts the output into probabilities. Each value represents the likelihood that the input image belongs to a specific class, such as a sneaker, coat, or bag. The highest probability becomes the model's final prediction. After you finish building the CNN architecture, the next step is to compile the model. Compiling is where you tell Keras how the model should learn and how it should measure its performance during training. At this stage, you are not training the model yet, you are just configuring it. You typically choose 3 key things. First, you select an optimizer, which controls how the model updates its weights based on the error. A very common choice for Fashion MNIST is Atom, because it adapts the learning rate automatically and works well in most cases. Second, you define a loss function, which measures how wrong the model's predictions are. Since Fashion MNIST is a multi-class classification problem, 10 categories, you usually use sparse categorical cross-entropy. This compares the predicted probabilities with the actual class labels and calculates the error. Third, you set metrics, which are used to evaluate a model's performance in a human-readable way. The most common metric is accuracy, which tells you how many predictions are correct out of the total. You use the model's fit method to train the neural network on your training data. You pass in the input data, xtrain, and the correct labels, ytrain. During training, the model goes through the data many times, called epochs, and gradually adjusts its weights to reduce error. While training, you can also provide a validation set, like x-test and y-test, so the model can be checked on unseen data after each epoch. This helps you understand if the model is learning properly or overfitting. When you click Run, the model starts around 81% accuracy and gradually learns until it reaches about 91% by the last epoch. After training the model, the next step is to evaluate it using the test data. This tells you how well the model performs on data it has never seen before. You use the evaluate function with your test dataset, x-test and y-test. You pass the test images, x-test, and their correct labels, y-test, into the model. The model then makes predictions and compares them with the true labels. It calculates the loss and accuracy on this unseen data. After evaluating the model, the next step is to make predictions. This means using the trained model to guess the class of new, unseen images. In Keras, you use the model predict function. To make a prediction using NumPy arrays, you first select an image from the test dataset, such as x-test. You then pass this image into the model using model predict, but before doing that, you expand its dimensions so the model treats it as a single input sample. The model returns an array of probabilities for all 10 Fashion MNIST classes. To get the final predicted class, you use NP-argmax, which selects the index with the highest probability. After that, you compare the predicted label with the actual label from y-test. For example, if the image is an ankle boot, the actual label will be class 9, which corresponds to ankle boot in the class list. Finally, you print both the predicted class and the actual class. If the model is correct, both will show ankle boot, meaning the prediction matches the real label. To view the image and make predictions, you can reshape the Fashion MNIST data and display it using mshao. First, you take an image from x-test and reshape it to 28x28. Because Fashion MNIST images are grayscale images of size 28 by 28 pixels. This allows Matplotlib to display it properly. Then, you use PLT mshao to show the image. After that, you pass the same image into the model for prediction. The model outputs probabilities for all classes, and you use NP-argmax to get the predicted class index. Finally, you compare the predicted label with the actual label from y-test and print both results. When you display the image using mshao and run the prediction, the result shows that the model correctly identifies the item as an ankle boot. This means the image you reshaped to 28x28 pixels is passed into the model, and after prediction, the highest probability corresponds to class 9, which represents ankle boot in the Fashion MNIST dataset. So when you print the output, both the predicted label and the actual label match. You have successfully completed the tutorial for TensorFlow. You learned how to prepare image data as tensors and how these tensors flow through a convolutional neural network. You built and trained a model, evaluated its performance, and made predictions on test images.